Welcome back, ladies and gentlemen. In this video, we'll look at thermal energy and efficiency. Okay, so first of all, just some lingo. We all know that things are hot, things are cold. We're going to talk about the difference between thermal energy, temperature, and heat. And they're similar but different. So just from a technical standpoint, thermal energy is really just energy stored as moving molecules. Faster molecules move, the more thermal energy things will have. Okay, so molecules get moving in really three different ways. We have conduction, uh, which are just bodies in contact, convection, when molecules are moving in liquids and gases, okay, and also radiation, and that's the transfer of energy with electromagnetic radiation. Okay, temperature. There are three different scales of temperature. Temperature, when we talk about that, it's really just the average speed of the molecules in a substance. Okay, there are really three scales, and I've grouped together Celsius and Kelvin for a reason. Celsius and Kelvin are over on the, I'm just circling them over on the right there. This diagram shows the temperatures for both the freezing point of water and also the boiling point of water. So for Celsius, we know that water freezes at 0, it boils at 100. Okay. The Kelvin temperature scale is the same as the Celsius scale, except it's separated by 273.15 degrees. Okay, so that is because 0 degrees Kelvin we talk about as absolute zero. And if we were theoretically able to chill things down that cold, that is the theoretical temperature at which molecules would cease to have thermal energy. Okay, so Celsius and Kelvin are separated by the same amount, like 1 degree Celsius is equal to 1 degree Kelvin. Okay, Fahrenheit is the anomaly, and Fahrenheit we'll talk about in just a minute here. So Celsius, if we're looking at finding Celsius given Kelvin, it's really just, they're separated by a difference of 273.15 degrees. Okay, Fahrenheit's a little bit different. Fahrenheit is that one that's really just in use in the States and some other smaller countries around the world. Fahrenheit, the freezing point of water in Fahrenheit is 32 degrees. The boiling point is all the way up at 212. So the separation of degrees is different for Fahrenheit than it is for Celsius and Kelvin. Okay, so if we're asked to convert some measurements, 5 degrees Celsius to Kelvin, to convert to Kelvin, we're really just going to add 273.15. So 5 degrees Celsius in Kelvin would be 278.15 Kelvin. Okay, for converting from Kelvin to degrees Celsius, we just go the opposite direction and subtract 273.15. So 257 Kelvin would be negative 16.15 degrees Celsius. Okay, the Fahrenheit to Celsius, this is for when you're traveling in the States and you hear on the radio, hey, it's going to be 80 degrees today. And you're like, what the heck is 80 degrees? And, you know, most of us in reality will be able to pump that into our Google device, and it'll tell us, it'll pump out a temperature for us. And this will just show you the math that it's actually going through to come up with that 80 degrees. The temperature in Celsius when you're pumping it into Google. Okay, so if it's 80 degrees Fahrenheit, first of all, we need to subtract 32. Okay, and then from here, it's a bit of a plug and chug, where that would be 48 times 5 divided by 9. So 80 degrees Fahrenheit. It's quite a nice day. That's 27 degrees Celsius. Okay, so that's the this formula. I just wanted to show you that to be like, hey, that's the formula that we actually apply to convert those two different measurement scales. Okay, heat or change in thermal energy. Heat is energy that flows as a result of a difference in temperature. Okay, heat is also known as a change in thermal energy, and I put that in the title because that's what heat is. Okay, our symbol for heat is either Q or heat energy, or E with the subscript H. The formula is on the screen: mc delta T. Okay, so EH is the thermal energy that is added to a substance, or the heat added. The units for energy, of course, are the joule. Okay, M is our mass of a substance. C is something new. C is the specific heat capacity. So specific heat capacity is unique to a substance, and that tells us how much energy is required to heat 1 kilogram of material by 1 Kelvin, or how much energy in joules is required to heat 1 kilogram of a substance by 1 degree Celsius, because 1 degree Celsius and 1 degree Kelvin have the same increment. Okay, and our delta T is just our change in temperature. And that can be in either degrees Celsius or degrees Kelvin. Okay, so here's we'll look at a couple of examples of how we apply this E is equal to mc delta T formula. Okay, if we have the thermal energy needed to raise 250 mils of water from room temperature, or from 20 degrees Celsius to the boiling point. First of all, we need to know the boiling point is 100 degrees Celsius for water. Okay, so some cool things about water. 1 liter of it is equal to 1 kilogram. 1 liter, which is 1,000 milliliters, is equal to a kilogram. And sorry, I should back up. What I'm trying to do is I'm trying to get the mass of water, given that our volume is 250 milliliters. Okay, so 250 mils, that is going to be equal to 0.25 kgs, and really we're just finding the amount of substance that we're heating up. Okay, specific heat capacities. I'll never ask you to memorize these. This is a data table thing. Here are some specific heat capacities for a few different materials. You'll see water's is quite high. It takes a lot of energy to increase or change the temperature of water. Okay, so just applying our Q, or heat energy, is equal to mc delta T. Okay, we're looking for the thermal energy. So our mass of our water is 0.25 kilograms. It takes 4,180 joules of energy to heat 1 kilogram of water by 1 degree Celsius. Okay, and we want to change our temperature from 100 from 20. So our change in temperature, this change in temperature is we're increasing our temperature by 80 degrees Celsius, and we need energy to be able to do that. So if we multiply 0.25 times 4,180 times 80, we end up with 83,600 joules, or 8.4 times 10 to the 4 joules. Okay, I just want to go back to this this formula here. So we have 0.25 kilograms of mass. So kilograms in the numerator, kilograms in the denominator. Those things will cancel out. And then also we have our degrees Celsius in the numerator, or our denominator, and degrees Celsius in the numerator. So we're left with units of joules in this question. So the thermal energy, or the heat needed to raise 250 grams of water from 20 to 100 would be 8.4 times 10 to the 4 joules. Okay, so what happens then if we mix some substances together? Okay, so here, if we're given a question, find the final temperature of 420 grams of 85 degrees Celsius aluminum, and we're given the specific heat capacity for aluminum. It's dropped into 200 grams of water at 15 degrees Celsius. Okay, what is going to be the final temperature, the final temperature of the combined mixture. Okay, so something that's true of all things is if you mix them together, they are going to end up coming to the same temperature or having the same final temperature. And we also know that the amount of energy lost, and here, this is our aluminum that is going to be losing energy because it's the hot one. It's going to be losing thermal energy, and it is going to be the water that is gaining thermal energy because it starts much cooler. So they're going to come to temperature somewhere in between. Okay. So the amount of heat that is lost by the aluminum, this negative that's out front, if we think of multiplying that negative into the brackets where our change in temperatures are, really our initial temperature and our final temperature, those just change, they change signs. So all I've done there is change the order that we write those in. And we're going to use the specific heat capacities that are given to us on the at the side of your screen. Okay, and then from here, we are going to plug and chug some numbers into this long formula. Okay, so on the left-hand side, we're going to have aluminum. So we have 420 grams or 0.420 kilograms. Specific heat capacity for aluminum is 903. It starts at 85 degrees Celsius. Okay, and our TF is what we're finding, our final temperature. Okay, water on the right side of our equation is 0.2 kilograms. Its specific heat capacity is 4180 joules per kilogram degrees Celsius. And then we'll have our TF minus our initial temperature that it starts at. Okay, so our final temperature of this thing will be 36.8 degrees Celsius. And then we'll just ask the question, does that make sense? Yeah, our 36.8, that's somewhere in between 85 and 15. So it makes sense that that number is within reason for what we're trying to find. Okay. Okay, so next, the topic of efficiency. So when we talk about efficiency, it's usually in reference to machines. So whenever we have machines, we're always going to have some input going in, and this is usually electricity. Usually electricity that's going in, and this work word can be work, it can be amount of energy that's going in. We can sometimes think of efficiency and power. But it's really just a comparison between an input and an output. Now, whenever we use a machine, the output that we get is never going to be equal to the input because we have this energy we always have some little bit of energy that is lost. And that's either due to friction or to heat. Okay, some amount of energy that we don't find useful, but it's just lost to our surrounding environment. Okay, so when we talk about efficiency, we talk about useful output as it compares to the useful input or the energy input of a machine. Okay, so again, this word power or energy, that can be work, that can be energy. Okay, it can be power. This one is the formula that you will find on your formula sheet. Okay, it's really a number that's stated as a percent, and it's just a comparison to how much energy out you get to, or as it compares to how much energy that goes in to a machine. Okay, here's an example. We looked at this one earlier. If we have how much energy or thermal energy is needed, well, we found this. It's going to be 84,000 joules of energy is needed to raise 0.25 kilograms of water from room temperature to the boiling point. Okay, then, well, what if we actually heated that water with a 1500 watt kettle for 2 minutes? So what's the kettle's efficiency? Okay, so with power, which is what we're given here, this is a unit of power. If this kettle has a power of 1500 watts, we looked at power before as work or the rate of doing work. So work is also if we apply work to something, we are going to change the energy that something has. So our change in energy divided by time. So really this change in energy is now what we're going to be solving for with the information that's given to us. If we know that our power of our kettle is 1500 watts or 1500 joules every second, that kettle is going to be running for 2 minutes. Okay, 2 minutes is 120 seconds. We know that the energy change, or the energy input into this thing, will be power times time, power being 1500 watts or 1500 joules every second for 120 seconds. We know that our energy, and this, I'm going to change the subscript here because our energy input, as I mentioned earlier, is oftentimes just the amount of electricity that's needed. And here it'll be 180,000 joules. Okay, so using our efficiency formula, then we can find out how much energy out over our energy input. We'll turn that into a percent. The energy output is what we found earlier. That's going to be our 84,000 joules. As a comparison to how much energy goes in, we find that number as a percent, and we'll find our efficiency of this kettle is about 46%, 46.7%. Okay, efficiency is just a comparison of your output to your input. Okay, we'll look at another example of efficiency here. What happens when we have a crane that operates at 15 kilowatts or 15,000 watts, and it lifts 700 kg weight 50 meters in 2 minutes. So the amount of time that it does that job in is 2 minutes or 120 seconds. Find the efficiency. So I'm going to need to know my energy input. I'll need to compare that to my energy output. Find that number as a percent. Okay, so my energy input is going to be the electricity that's needed. So that'll be power times time, 15,000 watts times 120 seconds. Okay, that'll be our 1.8 million joules. Okay, that is going to be our energy input. Our energy out, if we're looking at taking a 700 kilogram weight, we are raising it through a certain height. We're really just giving this thing potential energy. So the energy output is going to be our potential energy gained by this object, or 700 times 9.8 times 50. So our energy out is going to be, in this case, 343,000 joules. Okay, so if we compare that 343,000 joules over the 1.8 million that we put into it, and we find that number as a percent, our efficiency of this crane is going to be 19%. 19%. Okay, comparison between our energy output versus our energy input. Okay, can you give this one a try? A 1200 watt heater heats 500 mils of water. 500 mils of water will be half a kilogram. Heats that water. Oh, and this should be subscript. Your specific heat capacity for water is 4180. Heats it from 10 to 75 in 4.5 minutes. Okay, so part A, how much heat energy was added to the water? Okay, we can find that by Q is equal to MC delta T. How much energy did the heater use to heat the water? So our energy input will be your power times time. And then can you find the efficiency of the heater? Okay, and our Q, this will be how much energy we get out of whatever this thing that we're trying to do is. Okay, so and then can you find the efficiency of the heater? Okay, folks, if you can give the thermal energy and efficiency worksheet questions a try, that'll get you in good shape for where we're heading to next. Thanks, ladies and gentlemen, and we'll see you again soon.